Let's talk about one-sided limits using our limit laws. Some functions don't exist on both sides, like radical functions. We see this graph of the function square root of x minus 3, and anything to the left of 3, any x values smaller than 3, the function just simply does not exist over here. And that's because we can't take the square root of a negative number. Plugging in any number smaller than 3 would cause a negative inside the radical. So if we wanted to look at the limit as x approaches 3, we can't do it from the left-hand side. So remember our notation for one-sided limits. If there's a little minus following the value that x is approaching, we know we're coming from the left. So if we were coming from the left, there's no function for us to follow. So this function, this limit, does not exist for this function, not from the left. However, if we came from the right side, there is a function for us to travel along, heading towards the value x equals 3, and it looks like this function is sending us down to 0. So the value of that limit comes out to be 0. Piecewise functions are another case where we need to use one-sided limits to be able to evaluate limits of a function. So we're looking at the function f of x, which is made up of two parts. If x is less than 2, then we're traveling on this straight line defined by 4x minus 3. But if x is equal to 2, we are not on that line. We jump to the other curve, which is defined by x minus 3 quantity squared. So we have our piecewise function here. If we wanted to evaluate the limit as x is approaching 2, we would have to do this left side first, right side second, or vice versa, but we'd have to do it one side at a time. So let's start by looking at the left-sided limit. Approaching 2 from the left of 2, so 2 is right here. Let's change our color. If I'm on my function and I'm heading towards the x equals 2 values, it looks as though I'm approaching 5. So the left-sided limit is 5. If I am coming from the right side of x equals 2, then I'm on this curve heading towards that x equals 2 dashed line, and it looks like I'm approaching 1. We computed a left-sided limit and a right-sided limit. The two limits do not match. Therefore, we know the two-sided limit. Remember, no symbol means this is a two-sided limit. If the left and the right limits do not match, the two-sided limit simply does not exist. Let's take a look at another special case of evaluating limits. And these are the cases where if we do direct substitution, we get something that looks like a number divided by 0. We know that that's not acceptable, so we're going to try and work around it. Now, if I look at the limit on the left and I try to evaluate it, I can see that I'm approaching 2 from the left side. But if I plug 2 in directly, then I get the form of a number divided by 0. It doesn't really matter what the number is in the numerator. Dividing by 0 is not allowed. So we need to manipulate this using some algebra so that we can figure out where this is going. So the first thing I want to do is remember that we have seen something like this before. A number on top, 0 on bottom. I want you to think about vertical asymptotes. When we had vertical asymptotes, it was from a rational function where the denominator was equal to 0 at that spot. That's exactly what's happening here. We have a rational function and we are taking a limit that's causing the denominator to approach 0. The basic form of a vertical asymptote would be something like 1 over x to the n power, or we could even say 1 over x minus a to the nth power. And we came up with some general rules that said there's two things that could happen. The two cases are, is n even or is n odd? If n was even, we said that both sides of our limit were going in the same direction. Either they were both going up or they were both going down. But if they were odd, we said one side goes down, one side goes up, or the vice versa. So we need to see if we can manipulate this rational expression so that it looks like this general form to help us identify what type of vertical asymptote we're dealing with. So let's start with some algebra. I'm going to copy our function down, and I'm going to factor the denominator as much as possible. Now we can see that this does not simplify, but we can also see that we're going to have two potential values that could cause this denominator to be 0. So I'm going to rewrite this in a factored form. My numerator is going to go by itself, and then I'm going to factor my denominator and write each factor as its own fraction. The purpose of this is so that we can see which of these factors is causing the vertical asymptote. Now, this factor would cause a vertical asymptote at x equals 0. This factor causes a vertical asymptote at x equals 2. Since our limit is allowing x to approach 2, the x equals 0 problem is not really showing up right now. It's the x equals 2 problem. So I want to factor my function completely so that I can find the problem and isolate it. So I'm going to rewrite this one more time, combining the non-problematic factors times the problem. Now, if I were to apply the limit to the function as it is now, when I plug 2 into this front factor, I have no problems at all. I get 2 minus 3 on top, which is minus 1, and I get 2 on bottom. No problem. But when I go to apply the limit to the second factor, I see that I have an asymptote, and I know that that's going to cause me to have an infinite limit. So now I need to figure out what type of infinite limit is it. Is this going to positive infinity? Is it going to negative infinity? So to do that, we need to think about where x is coming from and what happens when we plug those numbers into our function. If x is on the left of 2, then I'm using numbers smaller than 2. So if I'm on a number line and I'm approaching 2 from the left, then I might be using numbers like 1.9 or 1.99 or 1.999, for example. If I plug these numbers into my function, 1 over x minus 2, I'm going to get a negative in my denominator because all of the values that I'm using for this limit are smaller than 2. So x minus 2 would give me a negative in the denominator. That negative is getting very, very tiny, which almost makes it look like a 0, but it was negative before it approached 0. So this must be going to negative infinity. So when we go back to look at our limit, we know that it's not going to positive infinity, it's going to negative infinity. And there was a factor of negative 1/2 out front. Negative times negative should give us a positive, so our final answer for this limit coming from the left would be positive infinity. And if we're not quite sure that we trust that, let's graph it. I've pulled up GeoGebra, our graphing program, and I'm going to type in f of x is equal to, it's a fraction function with x minus 3 in the numerator, and then x squared minus 2x in the denominator. Now we can see the full function. Let me thicken that line for us. And we can see that there's multiple asymptotes. We knew that there was one at x equals 0, and we also knew that there was one at x equals 2. And we were approaching x equals 2, so that was the vertical asymptote that we were dealing with. Now the function to the left of that x equals 2 value is this green curve. And if we're traveling along the green curve, moving towards x equals 2, we can see that our function is shooting straight up to positive infinity. These functions can be a bit tricky because there are multiple steps that we have to keep track of. If you notice, we did find an infinite limit, but the one that we isolated was going to negative infinity, and we multiplied by a negative 1/2, which flipped it around and made it go to positive infinity. Let's try another one. This function clearly has a problem in the denominator when x is equal to 1, and of course that's exactly where x is approaching for this limit. So we need to isolate that problem. This one will be a little bit easier to isolate because there's only one factor in the denominator. So let's write it as two separate terms. Now that we have it as two separate terms, we can apply the limit to each term using our limit laws. We can see that the first factor, the limit as x approaches 1 for x plus 1, that simplifies nicely to 2. It's the second factor that gives us the problem. We have 1 over x minus 1 squared. So we know we have a vertical asymptote at positive 1. And we know that we have an even exponent on that factor, which means that our function is either going up to positive infinity on both sides, or it's going down to negative infinity on both sides of our asymptote. If I'm plugging in positive 1, any number outside of that is going to be either a smaller number or a larger number. But when I square it, the minus that could have happened inside of these parentheses becomes positive. So I know that this limit is going to positive infinity. We're multiplying two positives so we can stay at positive infinity for our final answer. And of course, if we're not sure that we have it right, we can always graph it. So I'll leave that for you to do as your own exercise.